Welcome back to Numberholic. I'm your host, Sajari, and it's always a pleasure to have you here. Today, we're diving into the 19th episode of Proven, Yet Hard to Believe. In Zeno's Paradox of the Footrace, I first pointed out the importance of understanding the idea of speed. The key idea was that the paradox implicitly involves choosing numbers and defining ratios. That's the first important perspective to really grasp what's going on. From a mathematical point of view, we said the paradox only makes sense and can only be resolved if you precisely define the ratio between space and time, both of which can be divided infinitely. In the end, the paradox can be resolved by setting a ratio between two endlessly divisible things. But you can also maintain the paradox by changing that ratio. Today, let's move on to the second part of our discussion. What I want to focus on today is the idea of endless continuation, that is, infinite processes. Let's start with a comment from Professor Zeller, which we mentioned in the previous episode. He criticized how people often confuse the infinite divisibility of space and time with them being already divided infinitely. When we go through an infinite process, some properties can survive, others may disappear, and sometimes entirely new properties can emerge. Let's go back to Aristotle's wheel paradox. Imagine dividing a circle. You'll see that there's a clear 1-to-2 similarity. The smaller circle is exactly half the size of the larger one. Every point on the arc of the smaller circle maps exactly to one point on the larger arc. Now, divide it again. Still, we have the same 1-to-2 ratio, and the 1-to-1 correspondence remains intact. This process can go on forever because an arc can be divided infinitely. But what happens after this infinite process? After infinitely dividing the arc, what's left is just a single point. And all of a sudden, the 1-to-2 similarity? Gone. The property of the arc being twice as long? Also gone. The only thing that survives is the 1-to-1 correspondence. In other words, the property of length which belonged to the one-dimensional arc has vanished, and only the property of a zero-dimensional point remains. Why? Because infinite divisibility allows us to make the length smaller than any given quantity, eventually erasing it completely. You may have also seen this kind of claim related to triangles. The sum of the lengths of two sides equals the length of the third side. Again, same logic. Since a triangle's height can be divided infinitely, you can shrink it smaller than any given amount. This essentially erases the height, and with it, the property of vertical length. This is actually related to an axiom introduced by Archimedes. So what does this tell us? The result of an infinite process can be radically different from what we might expect. Let's look at a simple example from algebra. Here's a method for finding square roots that's often referred to as a Babylonian method. Let's try to find the square root of 2, starting with the number 1. Try it out. Amazingly, we're getting very close in just a few steps. Or take a simpler approach. All these sequences get closer and closer to the square root of 2 through an infinite process. And yet, every number in the sequence is a rational number. But the square root of 2 itself is irrational. So what happens? The property of being a rational number disappears. And instead, a totally new property, irrationality, emerges. So what's the takeaway? When something continues endlessly, it can lose the properties it had, and even gain entirely new ones. Does that idea fill you with wonder? Or maybe a little fear? The ancient Greek mathematicians actually feared this. In the next episode, before diving deeper into Zeno's paradox again, we'll take a look at a modern kind of paradox, one where the answer isn't determined by the problem itself, but by the process used to solve it.